So yesterday we were discussing about the normality tests, and we were we were about box plots, because box plot it actually helps us to understand that how the our data is actually distributed. Okay, so let's take a look at that how to construct a box plot. You can see that this is the example of a box plot. The particular scale is given here, the data set that has been provided to you. So you first determine the 5-number summary and first arrange the 5-number summary on a number line in the following fashion. That means from small to large, you arrange the numbers in order. That is the first thing. Okay, suppose you have been given this particular data. You can see that here it is like 5, 6, 12, 13, 15, 18, 22, and 50. So in this way it is provided. But haphazardly or in any order, you can be provided this data. So first, you need to make sure that your data is in order. Okay, from small to large. So you need to, after ordering the data, then you will be finding the quartile values. Okay, I have told you earlier that Q1, Q2, and Q3, these values are to be determined. So Q1 is termed as lower quartile, Q2 is termed as it is the second quartile, Q2 is the middle quartile, and Q3 is known as the upper quartile. Okay, so quartiles split an ordered data set into 4 pieces. So you can see that these 4 pieces. So you need to find out these values. So Q1 will be 6 plus 12 divided by 2. So it will come out to be 9. For Q2, it will be 13 plus 15 divided by 2. It will be 14. And for Q3, it will be 18 plus 22 divided by 2. It will be 20. Okay. So now you need to plot the data. And so how can you plot it? So you have taken this particular line of x-axis. Okay, so all these datas you have marked the Q1, Q2, and Q3 values. You have marked it. Okay, and then what you will do to find out the lower value and the lowest value and the highest value from the box. It is not I'm not talking about the lowest value or the highest value of the series. From the box, if you want to find out that, then first you need to find out these values, the Q1 minus 16.5. Okay, so how 16.5? Because you can see that this is a kind of you can say that these are the tolerances. Okay, you need to estimate the tolerances first. So the tolerances are given by The formula is Q1 minus 1.5 into IQR. IQR means interquartile range. And here the tolerance is given by Q3 plus 1.5 into IQR. Okay. IQR means interquartile range. The Q1 value is known. The Q3 value is also known. So you need to find out the IQR or the interquartile range, which is given by Q3 minus Q1. So it will come out to be 20 minus 9 is equal to 11. Okay. So now you put the value here 11. You put the value here 11. So the lowest tolerance or the lower tolerance that you can find out, which will come out to be minus 7.5, and the higher side of the tolerance that you can also find out, which will come out to be 36.5. Okay. And anything outside of the interval, it will be treated as an outlier. So you can see that from the interval is actually minus 7.5. The range is from minus 7.5 to 36.5. Minus 7.5 to 36.5. This is the range. This is the box plot. So you can see here in the data set, all the values lie within this range of minus 7.5 to 36.5 except 50. Okay, 50 is beyond this range minus 7.5 to 36.5. Hence, 50 treated as a, so the diagram will be like here. Actually, this diagram is wrong. The diagram will be, this is the box plot. The diagram of the box plot is correct, but the range, it is not correct. It will be, the range will be from minus you can see that minus 7.5. So it will, there will be something like that here minus 7.5 and plus 36.5. It will go like here, not here. Okay, so this diagram is wrong, and uh, you should actually uh, uh, remember this thing, because many times I have seen that this problem I have given in the examination, and it has happened that you have, most of the 99% cases it has happened that you have drawn this particular diagram and you have scored 0. So keep this thing in mind, that whenever you will, if this problem comes in your exam, then don't do this diagram. This diagram is wrong. Okay, but I have not made it correct because so that you can apply your common sense rather than going through all those slides, copying and pasting. Don't copy and paste. You must apply your common sense that this diagram is actually wrong, because you are getting these values, these tolerance values you are getting for the lower and the upper. So you must use those values while mentioning or addressing the box plot. Okay. So you can see that suppose these kinds of different types of box plots you can find. This is very symmetric in nature, and I have told you earlier the left skewed and right skewed. Okay, this is the left skewed. You can see that the tail is long on the left side, and here the tail is long on the right side. So it is the right skewed. Okay, and this is also known as positively skewed since it is left, and this is also known as, this is actually negatively sorry, this is actually uh, this is this is actually negatively skewed since this is on the left side, and this is actually positively skewed since this is located on the right side. The tail is on the right side. Okay. So from here, interpret the box plot. The first thing you have noticed in this example that you can determine the outlier, and you can also identify that the data is symmetrically distributed or it is left skewed and or right skewed. Okay, I have told you earlier that in case of suppose uh, here it is, you can see that that in case of right skewed or the positively skewed, okay, you can see that the mean is greater than the median. Okay, but in case of negatively skewed, the median is actually, it is greater than the mean values. Okay, so the here actually you can see that most of the data, okay, most of the data they will have the uh, they will have the less value as compared to the mean. Okay, and in another case you will have the more. Okay, so that will have the values of greater than the mean. So uh, that you can understand from this one. Okay, this box plot. Now the QQ plot, it is not required, only the box plot will suffice. You can directly now come to the point of chi-square distribution. This is another kind of distribution, but that we will discuss after the normal distribution. Okay. In the chi-square distribution, the distribution of the chi-square statistic is called the chi-square distribution. So in this lesson, we learn to compute the chi-square statistic and find the probability associated with the statistic. And we will work through some chi-square examples to illustrate key points. The example I will not discuss here because in case of hypothesis testing, we will give you the example of the chi-square distribution. Okay. The chi-square statistic. Suppose we conduct the following statistical experiment. We select a random sample of size n from a normal population having a standard deviation equal to sigma. That means it is actually sigma population. It is the standard deviation of the population. We find that the standard deviation in our sample is equal to S. This is actually known as the sample standard deviation. So given these data, we can define a statistic called chi-square using the following equation. So the chi-square will be given by, it is equal to n minus 1 into S square. That means the sample standard deviation divided by sigma square, the population standard deviation. So the distribution of the chi-square statistic is called chi-square distribution. And the chi-square distribution is defined by the following probability density function. And here also the degrees of freedom, these are provided. And this is and we use to indicate this formula, we use E or the natural logarithm system. Okay. So you can see that along x-axis we are representing the chi-square statistics, and along y-axis we are representing the probability values. Okay, so chi-square distribution, you can say that it is basically nothing but the distribution or of the different values of the chi-square provided the degrees of freedom. Okay. And basically chi-square distribution is used to compare uh, you know the two or more uh, uh, the variances that you can use in later on. We will see this thing I'm showing you, that when you will be using the hypothesis testing part, when you will cover, then we can we will see that here we can see that for comparing single population variances, chi-square test will be used for comparing single population variances. Or in other words, we can also say that chi-square distribution is used in the common chi-square tests for goodness of fit of an observed distribution to a theoretical one. Okay. So now uh, again go back to this point. Okay. Now after that, there is also F distribution. So the F distribution is related to chi-square because the F distribution is the ratio of two chi-square distributions with the degrees of freedom nu1 and nu2. The F distribution is a probability distribution of the F statistic. So in other words, it's a distribution of all possible values of the F statistic. Okay. The F distribution is a skewed distribution of probability similar to a chi-square distribution, but where the chi-square distribution deals with the degrees of freedom with one set of variables, the F distribution deals with multiple levels of events having different degrees of freedom. This means that there are several versions of the F distribution for differing levels of degrees of freedom. So you can understand that the F distribution is basically it is the ratio of two chi-square distribution having different degrees of freedom, and it is nothing but the distribution of different F statistic values, because along x-axis you are representing different F statistics. So this is nothing but the distribution of different F statistics values for different degrees of freedom. Okay. And it is basically used to uh, compare two or more the variances that we can consider. For that reason we can compare F distribution. And not only that, but also in case of ANOVA or analysis of variance, we basically compare more than uh, two means we can compare. And there also the F statistic can be used. Though F statistic basically compares variances, but in order to compare the more than two means, there also we can use the F statistic. So that those things we will discuss later, and also we will give you the example, both kind of examples we will provide, which is one is for absolutely for F distribution, and one example, another example, many examples we will see using the ANOVA or analysis of variance. Okay, so that we will discuss later. So now another thing, that maximum likelihood estimation we will discuss. Many a times you will hear or you will listen to this particular term, that maximum likelihood estimation. What is this? When we collect data from survey, depending upon the pattern and nature of the data, X variable, we choose the distribution. It means depending upon the problem, we basically choose the distribution, what kind of distribution we should use. Then we need to fit the data in that distribution in best possible way to represent the population. Okay, because I have already said that in inferential statistics we need to know the characteristics of the population, which can be done by using the sample. So the fitting of the data in that distribution in the best possible way, it is required. And for this reason, we need to estimate the maximum likelihood for the parameters, okay, mentioned in the formula of the particular likelihood function, because these parameters indicate the shape of the population distribution for that particular case in best possible way. So maximize the likelihood function and find out the formula for the parameters, then plug in the values collected from the survey in that formula to estimate the parameters. Now you can get your population distribution curve. Okay, so what does it mean? It means actually that whenever you are, suppose based on the problem statement or based on the nature of the data, you select a particular distribution, that is okay. But what kind of distribution is this? That means what will be the shape of the distribution, that that you should know. Okay, and for this reason, the probability density function or the likelihood function, you can maximize it and you can get the formula for uh, the maximum likelihood. Okay, and you just plug in the values for the from the sample survey, and you can estimate that what will be the shape parameters of your distribution. So let's take a look at the example. Okay, suppose uh, you think about suppose you have a particular data set. Okay, think about this particular problem. Okay, you can see that there are different types of curves are there. So all these are normal distribution, but all these normal distributions are not same because their parameters are actually different. Okay, and this is the maximum the probability density function of that. So similarly, for the exponential distribution, suppose you have got a data which is suitable for the exponential distribution. Okay, now the shape parameter of the exponential distribution can be defined by these parameter lambda. Okay, you can see that for the different values of the lambda, for lambda is equal to 1, for lambda is equal to 4, for lambda is equal to 10, for different values of lambda you can have different types of exponential distribution, you can see from here. Okay, now how your problem is that how can you understand that which particular, what will be your lambda value? How can you understand that which particular type of distribution, which particular type of exponential distribution is fit for your data? Okay, so that's why there is a particular formula. Suppose the lambda is given by, here you can see that n divided by x1 plus x2 plus dot 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 xn. Okay, so you have collected yeah, the data, the samples, you will be putting all those excess values, from your data set, how many data you have, so how many numbers you have, so that you also know, you put it here, the value of n. Okay, if there are 10 values in your data set, then you put here 10. If there are 11 values in your data set, you put here 11, and ultimately you will be able to find out your lambda value. Suppose your lambda value has come out to be 4, so you can understand that the distribution will be like this. Okay, now how to find out these values, this lambda value? So if we maximize y is equal to lambda into e to the power minus lambda x, this is the probability density function or the likelihood function for the exponential distribution. Okay, the values of x, or the time between two particular events, that is actually mentioned here. So if this function is, it is nothing but the function. Okay, so if this is the given, so you can find out from here, you can maximize it, and ultimately you will be able to find out the lambda values. So the thing that I have shown for this particular example, or for this particular exponential distribution, the same thing can be applied to the other distributions as well, for normal distributions and for the other distributions also. You can find out the maximum likelihood. Okay, so you can check out, there are many videos are links are provided here. So these values you can also check to understand more about the maximum likelihood estimation. Okay, so now we will discuss a very important topic, which is known as the regression analysis. Okay, so it is a statistical procedure used to find relationships among a set of variables. Okay, you already, I have discussed about the dependent variables and independent variables. Okay, so in order to understand the relationship between the dependent variable and independent variable, you can use the regression analysis. But before discussing the different types of regression model, let's take a look at the example for a simple linear regression. It will make your idea clear, and we can go through the different types of regression model. So first, take a look at discuss about the simple linear regression. So suppose you are a vet epidemiologist for the county cooperative, and you gathered the following data. Okay, so this is the food intake by the cows 4, 6, 10, 12, and the corresponding values for the milk yield, that is also provided 3, 5.5, 6.59. And the question is that what is the relationship between cows food intake and milk yield? Okay, this is the relationship that you actually need to find out. Okay, so the regression equation in this case will be provided by y is equal to beta 0 plus beta 1 into x1. Okay, but before that, you can also plot a scattergram. You can graphically plot it. Okay, milk yield, this is actually y, because this is your dependent variable, and here the food intake, it is actually x or x1. This is your independent variable. So along x-axis you are representing your food intake x values, all the independent variables, and along y-axis you are representing your dependent variables or the milk yield. Okay, so 4 comma 3.0, 6 comma 5.5, 10 comma 6.5, 12 comma 9, all these values you are plotting in the graph, and the relationship will be given by y is equal to beta 0 plus beta 1 into x1. This is nothing but the formula that 12th standard, the formula for the straight line y is equal to mx plus. Okay, so c is here the beta 0, which is actually a constant term, and m is here the slope. That means how the values are changing depending upon the for per unit increase in the x values, how the y value is changing. That is actually meant by the slope or the beta 1 value, okay, into x1. So your objective is to find out the values of the constant and the coefficient. Okay, so these values you will be finding out. So beta 0 value here, suppose the beta 0 value has come out to be 0.8, and the beta 1 value has come out to be 0.65. Okay, so this is your will be your regression equation for this relationship, that y is equal to 0.80 plus 0.65 into x1. This will be your regression equation depending on this particular sample. Okay, so now we can go back to the type of regression models. Okay, so you can see that here actually mm, uh, there you can see that this is simple linear regression. This is one kind of thing. Why this is a simple linear regression? Because you have one dependent variable here and you have only one, you have also one independent variable. So this is known as simple linear regression. But in case of multiple linear regression, what you will find that you will have one dependent variable, but instead of one particular independent variable, you will have several independent variables. Okay, so uh, this is that will be applicable not only x1, also you may have x1, x2, x3, a lot of independent variables, several independent variables will be there, more than one independent variables will be there, which will be treated as multiple uh, regression. Okay, now again they can be classified into linear and non-linear. Okay, simple and as well as multiple. Here you actually assume in case of in this for particular data, if you plot this data, you can assume that more or less, I'm not saying exact, but more or less the nature of the relationship is linear, you can see. But there are some particular problems where you will find that simple, I mean linear assumption is not actually good. The assumption of linearness is not applicable. In those particular cases, you can use, you should use the non-linear equation. It is actually, it is a bit difficult in nature, because non-linear regression, it is not very easy, because among non-linear there can be different types of relationships. Not only, you know, it may be quadratic, uh, to the power, I mean square, or to the power 3, 4, many types of things can happen in case of linear. Okay, so how to understand that whether data is it is linear or non-linear, so that I will discuss later. Okay, and I can also show you some multiple linear regression analysis. Okay, so that I will show you. Okay, some YouTube videos links are provided. Okay, so these are the classification, in general, these are the classification of regression. Apart from that, there is also another type of regression, which is known as a logistic regression, that I will discuss also later. Okay, because here you can see that in these cases, your the y values or the dependent values, it is continuous in nature. Any kind of rational data uh, you may have, but there are some cases where you can have the dependent, the data value can be for example 0 or 1. Okay, or it may be discrete in nature. Okay, so in those cases the logistic regression can be used. Okay, so we will discuss those things also, but here actually you don't need to worry too much about it, because all these things can be performed using Minitab software. I will provide you obviously the link of the Minitab software later. Okay, uh, as of now, I'm not discussing about the logistic regression, but later I can discuss about the logistic regression equation. Okay, so now you need to find out that what are the formula for the beta 0 and beta 1. Here you can find out that there is some formula for beta 0, and this is the derivation of the intercept, and this is the derivation of the coefficient. These derivations are not required, just to give you an idea. I have given you that the partial derivation have been done for the derivation of intercept and the derivation of coefficient, how this uh, uh, actually how these values we can get, but we should have the understanding of this. Okay, you can see here that we have already plotted the data. Okay, we have plotted the data as per the data given in the problem. That way we have simply plotted the data. Okay, now what is the equation? Suppose now here we are drawing the linear regression line. Okay, suppose this is the linear regression line. Okay, actually the regression line. The regression line means this is the best fitted. Best fit means difference between actual y values and the predicted y values will be where it will be minimum. Okay, so this is, suppose this is your the regression equation. Okay, y is equal to beta 0 plus beta 1 into x. Okay, now suppose, so what you can see, if this is your regression equation, then what will be the predicted value? So obviously this will be your predicted values. Okay, because all these points lie on this particular line, but they are corresponding to these values. Okay, so these points will be your values based on the regression. Okay, for example, suppose uh, you know this equation you have got. Okay, now if you place here suppose 4, then you will get a y value. This will be your predicted value for the first run, and this is your actual value 3. If you are asked for the second run 6, you'll be getting something. Okay, so y value, so that will be your predicted value, and your actual value will be 5.5. This will be your actual value, and the difference between the actual value and the predicted value for each and every run, that will be known as the residual. Okay, that will be known as the residuals. Okay, so are going to find out all these you are able to find out all these values. Now these is actually known as your the error terms. Okay, the difference is actually known as the error terms. Okay, why we are saying it error terms? Because actually here in general it is represented, and it is represented population wise, but there is a difference between the error and the residuals. Okay, see, whatever we are doing here, suppose these values have been provided and you are dealing with this particular values, so this is just sample you are taking, but you don't have any idea about the population. Okay, so the regression line that you are considering, This is actually, it is representing the population line, but practically when you will be dealing with the case study or particular survey, you can never have a regression line based on the population. Okay, the regression line that you can draw, that is only based on the your samples. Okay, so the predicted value that you will give or you will find, that will be also based on the sampling. So the difference between the predicted value and the actual value that you will get, that is only the residuals. But the no, you don't have the idea about the population, so you cannot find the regression line based on the population. So the actual difference between your observed value and the predicted value, that you can never know. You can never know the error term actually. Okay. So this is the basic concept, and here how they are represented, what are the terms, so those things are also given. So based on this equation, okay, here actually we can simply we could have taken just the difference, but the difference it is squared, so that there is not some negative term. So that's why they have been squared, and the LS minimizes the sum. Okay, so then by this, okay, so if you make error squared, then it will be also error squared. Okay, so you can values, these values you put here, and ultimately you will be getting these kinds of terms. Okay, and if you do the derivation or the differentiation, the partial derivation you can do, you will be getting these values. Okay, so automatically the values for your the intercept. Okay, and also the slope value, intercept, that means the constant term, on the slope value, that you can get the formula. Okay, and in this particular formula, suppose this formula is given. Okay, and you can see that from this table, okay, they have calculated all these values: x square, y square, the summation of x square, summation of y square, x into 1, summation. These values they have calculated in the table. They have put these values, plugged in these values, and they have calculated all those things. Okay, and finally they have got the beta 0 values and the beta 1 values. They have got it from for 0.65 and 0.8. They have put these values here, okay, to get the equation. Okay, and this is the multiple linear regression equation, but and we should also know that particular R squared values and many types of estimates are there in order to understand that how closely the variables are related with each other, that we will discuss in the next class. Okay, so now I am going to stop the recording.